9, 9, 9, 9, 9. So 9, you got to use product rule. And you didn't have to do what I did, but I knew when I was going to take the product of this, I decided to just expand it, but you didn't have to. So I expanded it here, and then I tried to color code. So first times derivative of the second plus the second times derivative of the first, and then I just combined. So when you multiply these together, you get that. And when you multiply these together, you get this, because remember, this green thing just came from that natural log expanded, so I just condensed it back. And that was it. Yes? This one? This one. So do you mean this green or number 1 or number 2? So number 2, the green here, because remember it's product rule, so product rule says first times derivative of the second plus the second times derivative of the first. So I just copied it down. Does that make sense? Or, whoop, can't write on my computer. Zoom. If we think of this as u and this as v, this is u v prime, and this is v u prime. Any other questions? Yes? Because it is a quotient. So the original problem, we had to use quotient rule because it's something divided by something else. So it has to be quotient rule. No, you don't have to. And this is actually not a hard one to take the derivative of without expanding. I just chose to. But yeah, I mean, you never have to expand. It will never make it harder. It just sometimes makes it easier. Say it again. Well, all that happens is this green, this green right here would just stay like the blue. And then when you take the derivative of the green, actually no, that just stays the same. Right here, when you take the derivative of the green, it would be taking the derivative of this. And just remember, when you take the derivative of a natural log, 1 over the argument times the derivative of the argument. But when you simplify this, 9 over 3 gives you 3 over 1. The x's cancel out, you have 1 x left. So you still get the same answer. Any other questions? Can I have your homework then? Yes! And who's ready for a reality check that doesn't count? Except we're not going to have one.
Really?
Yeah, I'll just combine it with the next one. No. Don't you worry. Thank you. And thank you.
Like both of those.
Yeah. It's kind of like I collect homework at the beginning of every class. We are going to jump right into our notes, so let's do it. And I'm going to make you guys do some work today. I'm tired of doing all the work. It's time you guys, did your share. Oh, yeah. Yeah. So we're going to talk about exponential functions. And we're going to do probably the hardest, we'll get it out of the way, but today will probably be the hardest formula that we're going to see all year. So we can do it, though. So we are trying to go, the theme from, oh my goodness, it's already starting today. Our goal for today, we're going to, like it says, we want to do integration and differentiation of exponential functions. So let's just do the most basic one. What is the derivative of e to the x? Well, to answer this question, we're going to use something that we already know, which is we know how to take the derivative of natural logs. So we will start off with this. The natural log of e to the x. By the way, what is the natural log of e to the x? Because this can simplify. Trey? It's just x. Exactly. Remember, logs and exponents are inverse operations. And so when you have a log and an exponent in the same problem with the same base, they just cancel out. That's why we have x. And you can also convince yourself if you're like, well, what is this? I don't get that. Remember around the world and how to rewrite your logs? You start at the base, and there's an invisible base of e on the log. And go around the equal sign. E to the x is, oh, e to the x. Oh, look at that. So any questions why this statement is true? You got to buy into this statement before we can move on. Because now we're going to take the derivative of both sides. We're going to take, I'm going to go back to a pen. We're going to take the derivative of the natural log of e to the x, and we're going to take the derivative of x. Now the right-hand side is easy. What's the derivative of x? 1. We'll just get the easy one out. Now, the derivative of the natural log of e to the x, we can sort of do. I mean, remember, to take the derivative of a natural log, it's 1 over the argument times the derivative of the argument. So 1 over the argument times the derivative of the argument. We just don't know how to find the derivative of e to the x, so I can't actually do that yet. But this gives me an equation now to solve for the derivative of e to the x. If I multiply both sides by e to the x, on the left, we're just left with the derivative of e to the x. And what is 1 times e to the x? Whoa. The derivative of e to the x is itself? Yep. This is it. So what's the derivative of e to the x? What's the second derivative of e to the x? And if you take the derivative again, what do you get? What's the 50th derivative of e to the x? Yeah. All right, maybe it's not the most difficult formula. We'll see all year. That's it, though. This is it. Yeah. So we are going to summarize this now. There, we'll put a little extra with it. Of course, like, wouldn't that be easy if it was like, that's it. That's all we're doing today. The derivative, your homework is just going to be 50 problems of find the derivative of e to the x. How many guys would actually do it if I just gave you 50 problems that were exactly the same, but they were all really easy? Would you say, screw this? What if I gave you 100 of them? Would you want to do all 100? I know, right? Binge watch Netflix while you're just writing on your paper. It's like, I will always do my homework. I will always do my homework. They don't make you guys write sentences anymore, do they? We used to have a teacher. Oh my God, I wish I could remember some of her sentences. She was an English teacher. If you have any older siblings that went here, ask them if they ever had Miss Churchill, and ask them about Miss Churchill sentences. So, like, if you, I think she had one for chewing gum. She had them, like, for little things things that wasn't really worth a referral to the office, but she'd make you write sentences. And I think at first, she started with 10 sentences, and then if you didn't turn those in, then she doubled it, and she doubled it, and then I think by the time I forget, at some point, it was either like 40 or 80 sentences. If you still didn't do it, then she wrote a referral. But her sentences, now she's an English teacher, so they were grammatically correct. They were not run-on sentences, but they were almost like a paragraph. They were so long. So I can't remember if she started at 5 or 10 sentences, but you may think, 5 or 10 sentences, that's not bad. 3 pages later, front and back. I loved them. Anyway. Differentiation. You know how I like my clouds. Differentiation, we haven't even talked about integration, but I think we're ready. I think we can just jump there. Differentiation and integration of exponentials. So, we just said the derivative of e to the x is e to the x. Now, I feel pretty confident that I can make this jump. If we know this is true, can you guys tell me what the integral of e to the x dx is? Oh my gosh, yeah, see, I had confidence in you guys. You didn't let me down. Exactly. And then we are going to put one more here. Just remember about chain rule. So if we're taking the derivative with respect to x of e to the u. Now this one will be kind of a stretch. I'm not going to joke about this being as straightforward as the other ones. So does anybody want to try this one? It's not that hard, but it's just not a no-brainer like the ones above. Remember, it's just chain rule. So if you're like, wait, what? Just chain rule. Marcus? Exactly. E to the u. Remember, take the derivative. In this case, the outside is like our exponential. And then our inside function is the exponent, so we have to multiply by the derivative of the inside function. So that one may be a little weird. And that's it. Those are our formulas for today. Now we're just going to do lots of problems to practice. Yes? Oh. Look over there! It's right there. Yes, thank you. What, me? No. Damn it, Andrew, you're not supposed to turn me in. All right. So, any questions on these, though? Because now what I'm going to do is I'm going to give you 4 derivative problems to work on. Work on them together if you want. I encourage it. Move around if you want, because I know we got people have left us or people are absent, so we have some holes in the room right now. So feel free, move around. We're going to do 4 derivative problems, go over them, and then I'm going to do 4 integration problems, and we'll go over them. So here are your derivative problems. And I will pause the video. So if you're watching the video, pause the video and try these on your own. All right, we can do the first one together, just to give you a little hint. Or if anybody wants to tell me what you got. But just the first one. Anybody have an answer for the first one that they want to share? Rena? Say that again? I just heard the negative. That is it. Excellent. Perfect. So, e to the u times the derivative of u. That's really all you do with it. Any questions on that one? Now don't forget, you may have to use product rule or quotient rule or something later on, but that's the idea behind it. So I'll give you a few more minutes to think about these. All right, it's 8:35. Are we ready? So we already did number 1. There's number 1. Here's number 2. So product rule. And you don't have to put your answer factored, but we often do, because if you recall from last semester, remember a lot of the things that we do with our derivative is we try to find critical numbers. We try to find where it's 0 or undefined. And to find where it's 0, you factor. So it's usually most helpful to have it in a factored form. So make sure, again, unless the directions specifically say to factor your answer, you don't have to put your answer in factored form. But make sure you know how to factor in case it's multiple choice, because if it's multiple choice, it's most likely going to be factored. And you have to factor to find the zeros. So any questions about number 2? If you didn't catch it on the 3rd line, I'm just reversing the terms, so I'm not starting with a negative. It's nicer that way. At least I think it is. So any questions on this one? I see some people writing, but I don't know if they're writing this one down or something else. Ready for number 3? Number 3. This one's pretty easy. I heard somebody talking about it. You don't have to use quotient rule because the top and the bottom are not functions of x. If you don't have your variable in the top and the bottom, it's not I mean, it could be quotient rule. You can do it that way. But you can also just treat it as a coefficient of 1/2. And it's easier that way. So it's almost its own derivative. It just changes a minus to a plus. And then there was number 4. So any questions, though, on number 3 before we look at number 4? Does anybody want more time writing down number 3? Okay. Jewel got it. Alrighty, here is number 4. So remember, number 4 is the fundamental theorem of calculus. I'll go ahead and walk through this one. I'm going to use a laser. I keep forgetting about this, like with the recording, that people can't see me point to the board, so I'm just going to use the little laser. Actually, here, ooh! I don't know if that'll be more annoying, but anyway, when you're going to take the derivative of this integral, remember, the derivative of an integral. Think fundamental theorem of calculus, part 2. This is the one, though, that uses the extension, because the limits, they are functions of x. They're not, like the bottom is not just a constant. So remember what the fundamental theorem of calculus says. It says evaluate the argument at the upper limit times the derivative of the upper limit. And then minus the argument evaluated at the lower limit. Times the derivative of the lower limit, but that's just 1, so I didn't write it. And then I just made it look nicer in the 3rd line. So any questions about that? Alrighty. So I definitely see some people writing this down. So our next 4 problems are going to be integration problems. Yes! Integration. Anybody still need this one? All right. Here are your integration problems. Good luck. I shall pause the video now. All right, so let's look at 5 together. So for number 5, I mean, unfortunately, I can't tell you this is what you always do to solve integration problems, because integration problems just don't always follow nice rules. Sometimes you just got to play with all the different things that we know. But one general thing is, again, we got a composition of functions. Let's try letting u equal the inside function, although what's inside and what isn't. But let's let u equal the exponent. That's a good place to start when you got exponents in your problem. So we're going to let u equal 1 over x squared, which, remember, you can think of as x to the negative 2. So what is du? Excellent. Yes. And it does seem like some of us still need practice with u substitution. So definitely, if you're having trouble with it, let me know. That I can easily make a worksheet with a whole bunch of different u substitution problems. I have a program that can easily generate those. So now, remember with u substitution, you're trying to represent everything in the problem with u. So see what you got right now. Sometimes you have to go a little further, sometimes you don't. So we have let u equal x to the negative 2, and that's found right here. So that will take care of that x in the top. We found that du is equal to all of this. Actually, I shouldn't highlight that yet. Do we have negative 2 e to the negative, or sorry, negative 2x to the negative 3 in the problem? We have close though, don't we? What don't we have in this? The negative 2. So I'm going to put the negative 2 on the other side. Make it negative 1/2 divide. And then, let's see what we got. So then we have something that can replace e to the negative 3 dx. Oh, that takes care of all of our x's. So we don't have to do anything else. We're ready to substitute. You know how sometimes we do this and we still have leftover x's? Sometimes you do, sometimes you don't. So now we're ready to substitute. So the blue part is going to change to u, and all that pink part is negative 1/2 times du. So any questions about this? So what's the integral of e to the u, du? Yeah. This is going to be e to the u plus c. And once we do the integral, then we can replace all the u's with what we let it equal. And that is our answer to number 5. So any questions on that? Now, I'm not saying all of these problems are u substitution problems, but they could be. Some of them are. So just think about that. All right, I'm going to go ahead, pause the video again, let you guys keep working. Okay, so number 6. Yes, the trick was there's really no work. The derivative of the bottom is in the top. We already found the derivative of the bottom in the previous set, but it's also easy to look at it and see. So it's just the natural log of the bottom. So any questions about that? Alrighty. So then this one, number 7, some of you guys I know I saw did it without doing any u substitution, and that's totally fine. Because this one's really easy to see that you have the derivative of the exponent in the problem and there's nothing else. But also just another general rule of thumb, and this isn't just for exponentials, this is for anything. If you're at a loss of what to do for an integral, but you do happen to notice, hey, I see the derivative of part of the integrand somewhere else, that's a good clue that u substitution is probably going to work. And hopefully, if nothing else, you noticed the derivative of this, the exponent, is right there. So let me let u equal that. So I can find du. Oh, and then I have everything I need for the problem. Yes? Well, that would just, you're basically doing this in your head. So any questions about number 7 before we look at the fun one? Yes?
Well, where did you get the e to the 4?
Oh. Where did my u look like a 4? Oh. You're talking about one of these?
Yeah.
Yeah, I don't think I can make my u look any better. But yeah, those are u's. I'm not very good. All right, you guys ready for number 8?
Yeah.
All right, let's do it. So here was the problem. So the very first thing is you want to take the integral. Now, I didn't actually use the integral symbol, but find the antiderivative of each part. And, oh, I guess I did. Ha, 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 ha. So the integral of this, well, the antiderivative of sine is negative cosine. And I didn't show any work for this, but if you look at the 1/2 e to the 2x, and you were to take the derivative of it, you'd have e to the 2x, but then you'd have to multiply by the derivative of the exponent, would cancel out with that. But you can do u substitution. But any questions where this part came from? But don't forget that plus c. By the way, with the words on this, we looked at this, but it's just been a while. Remember, particular solution means you're going to be able to find the value of c. If I ask you to find the general solution, that means you leave plus c, particular solution. Particular solution, you have to be given something like these points that I gave you, but you're given something to find the value of c. So, yeah, I got to plug in. Now, because that one's the first derivative, I plugged in the condition with the first derivative and found that c was 1. So now I know the first derivative. And then I basically do the process all over again to get to the function. So I'll stop there, though. Any questions just to that point? Before I scroll up, does anybody want me to leave it here first? I think so. I see people writing. Yes, David. Yeah, so, if you can speed things up a little bit, it definitely helps. I'm basically taking the integral of e to the 2x using u substitution. So I let u equal 2x, so du is 2dx. I don't have a 2, though, so I'm just going to move that over here. So then I can say 1/2 e to the u, 1/2 times the integral e to the u. So I did all that fast, but does that make sense? So basically the thing is to see, oh, let me look at the derivative of this exponent. It's 2. I really need that in the problem to just be done, but I don't have it, so I know I'm going to need the 1/2. Yeah. Anybody need this before I scroll? All right. So then I just, like I said, integrate again. And I get this. And remember, when I integrate this term right here, this guy right there, I'm going to have another 1/2. So that's why this turned into a 1/4. But now I have another c. So I plug in again. And I will find c. It's just going to be 0 in this case. And so the grand finale is that. Let me know if I scrolled too far, if anybody needs me to go back at all. But that is the end. So you can see derivatives are much more straightforward. Integrals get a little interesting. Because there's so many rules. And it's not as, that's where, honestly, it takes practice. Like I've said before, I know I've said it before, but I'll say it again. So it's been said that derivatives, differentiation, you're just following rules. But integration is more like an art. Because you have to be able to look at it and see how to do it. And that's where the practice comes in. So that is it. That is it for our notes. I'll leave that up there. I'm going to stop the recording and